Hello everyone, my name is Tianren. Today, I'm presenting our paper, Gemini, an example framework for bandwidth estimation in web real-time communication. This was in collaboration with Hongyu, Renyu, He, Shushu Yi, and Ding Wei Li in Nanjing University. My advisor is Jiaqi Zheng. Gemini is the first solution for the grand challenge on bandwidth estimation for real-time communications. The main goal of this grand challenge is to design and implement a bandwidth estimator on the receiver side of a provide RTC system, Alpha RTC. Alpha RTC is a fork of Google's Web RTC code base. In this challenge, OpenNetApp provided Alpha RTC engine for reinforcement learning. And at the same time, they also give a limited number of network traces. The traces are measured in real environments such as 4G, 5G, and wired network environment. The model is scored mainly by the quality of audio and video and network performance metrics. In fact, this evaluation system requires us to provide as smooth and fast bandwidth estimation as possible and reduce latency and packet loss. Real-time video applications never played a more critical role in our lives as it enables us to live and work remotely while staying connected with the rest of the world. In fact, web real-time communication, WebRTC, is widely used in areas such as enterprise communications, social applications, healthcare, and education. It is used in everyday applications like Slack and Messenger. However, the rapid increase in the use of the real-time video also poses an unprecedented challenge for consistent delivering high quality of experience, such as high video and audio quality, low delay to all users. A pivotal algorithm to optimize the QoE for real-time video communications is bandwidth estimation. It runs on the endpoint of a real-time video communication and aims at adapting the video bitrate dynamically to stay within the available network capacity. Bandwidth estimation is actually similar to congestion control problems. To solve such problems, the initial idea was to use rule-based algorithm. Google Congestion Control is one of these algorithms. In recent years, learning-based algorithms, particularly reinforcement learning-based algorithms, are developing rapidly. These algorithms train the neural network by learning the data generated by real network sampling, and some further adjust the neural network through online optimization, such as PCC family, PenSip, and so on. Some adopt hybrid learning method, incorporating rule-based methods into their learning, such as ONIR. These algorithms have achieved certain results and becomes reference in our work. In our work, we consider that rule-based algorithms can help learning-based one. Rule-based algorithms predict bandwidth based on aggregated RTP feedback packet information. These algorithms tend to elaborate state mechanism and therefore have good convergence. Compared to learning-based algorithms, the overhead of state calculation is much lower. However, they fail to achieve consistent high performance in complex and diverse network environment. Learning-based algorithms predict bandwidth based on neural networks trained by huge amounts of data. Deep neural networks tend to give it strong adaptability to network. However, training neural networks requires a lot of data and takes a lot of time and difficult to converge. Deep neural networks requires metric computation and bring high overhead. In fact, bandwidth prediction should not take up too much computing resources. At the same time, reinforcement learning is not so safe and is not very robust in an untrained environment. It's not difficult to find that the shortcomings of the learning-based approach can be remedied by rule-based algorithms. Based on this idea, we propose our framework, Gemini. The core idea of Gemini is that we can take advantage of the DLL excellent performance for a given environment while keeping the DLL stable inherited from GCC. In our framework, we mainly predict bandwidth through two models, DLL part and GCC part. We used trivial algorithm for DLL training and refer to WebRTC source code to implement the Python version of GCC algorithm. After receiving the RTP packet, we will predict the bandwidth through these two parts, and then through the overload detector, we can judge whether the current network environment is safe for DLL. If the environment is safe, we use a DLL estimates. Otherwise, we miss the results of the DIR and GC parts. The exact ratio is determined by the trust window. We use a hybrid estimation as a result. In the DIR part of Gemini, the most important is the design of state, action, and reward function. We choose receiving rate, packet loss rate, average RTT, latest prediction, and the difference between the current estimated bandwidth and the previous one as the state according to the information provided by RTP packets. After receiving the state, the DIR model will calculate the action according to the internal neural network and give it to the environment. We use a log-based function to normalize the actions. After the action is performed in the environment will compute the rewards through the reward function. We hope that the design of the rewards will enable the model to predict low latency, low packet loss rate, high receiving rate, and less drastic changes. In the specific interface of the challenge, the bandwidth needs to be predicted every tenth of milliseconds. As a result, we use a lightweight critic neural network. The top part is a Alter network and the bottom part is a critic network. In practical training, networks of this size can adapt to different network types. PRDR is not safe because of its black box neural network. It may have unstable performance under the condition of inconsistent training environment and operational environment. Our solution is that we detect the overload signal or the unsafe signal and combine the DIR result with the GC result. The core issue now becomes how to take advantage of the performance of DIR as well as avoid the unstable performance. We use a overload detector, which is based on the delay gradients based mechanism and dynamically updates the threshold. This design has similar implementations in both standard version of GCC and ONIR. In addition, we use the trust window mechanism to adjust the proportion of DIR and GCC results. When the state is unsafe, we use the trust window to control the hybrid estimation. If the latest AM signals are safe, the trust window will be increased by 1. Otherwise, it will be decreased by 1. By doing this, we can gradually use DIR data as the environment becomes safer. At the same time, when the environment is not safe, we can gradually shift the results toward GCC. We also use some tricks in training to improve the model's ability. OpenNetLab only gives us a limited number of network traces. These data are completely not enough for DIR model training, and we found some extreme data such as the zero rate that might be caused by unstable connections is not conducive to the convergency of the model. Therefore, we finally choose to generate data similar to the original data sample distribution. In the process of the generation, we carried out data cleaning and removed the data that was too large or too small. In fact, the generated data trained models actually perform better than the models trained by real data when tested. We think this trick is also an important part of our implementation. Here are some details of how we implemented Gemini. In addition, we did some experiments to preliminarily verify the effect of the Gemini. Gemini is actually a compromise between the DIR and GCC. We reduce latency relative to the DIR method and increase the speed relative to the GCC method. Gemini can reduce 95% higher delay by 28% than DIR under 4G networks with 700 kilobytes per second capacity. And here is a summary of our work. We plan further improve the overload estimation mechanism in the future and combine some methods of packet processing with traditional algorithms during DIR operation. Thank you.